Okay, in this video I want to talk about vector basics. And this is going to be part one of at least, I don't know how many, more than one. So, in no particular order, I may skip around a little bit. I'm going to talk about vector addition, both graphically and algebraically, scalar multiplication, finding components of a vector, and then finding a vector representation that goes from a point A to a point B. Well, first off, what is a vector? A vector is basically just a quantity with both a direction and a magnitude, okay? So, typically we represent vectors with just little arrows, okay? So, that's typically the way that we draw vectors when we do it graphically. Okay, so, one concrete example of something that you could use to represent as a vector would be wind velocity. So suppose, I've got it in the little xy plane. Here's a vector at the origin, and it's pointing not quite northeast, but in a northeasterly direction. So the idea is the magnitude of the vector is related to its length. The longer the vector, the bigger the magnitude. The shorter the vector, the smaller the magnitude. So this vector to me says, okay, if you're at some point, on a map, it says the wind is blowing almost northeast at some speed. Notice this vector over here on the left. Okay, so maybe I'll denote this vector. Typically, we give it a letter. A lot of times in books, they'll make it bold. It's obviously hard to make markers look bold. So sometimes to denote a vector, they'll also put a little bar over the letter. So there's my vector v. Maybe I'll call this the vector u. Okay, notice vector u is in a different place on the map, but notice it kind of has the same properties in the sense that it goes 2 units to the right and 3 units up. So in that sense, they're pointing in the exact same direction, and they have the exact same length. So this is an important property about vectors, is they're kind of independent of their position in the plane. So actually, we would say that vector u and vector v are really the same vector. They've got the same length, and they've got the same direction. Again, I say length and magnitude I'm going to use interchangeably. So they have the same magnitude and the same direction, they're equal. And maybe one other little vector. Maybe I've got a vector that's kind of pointing, to the southeast. So to me it looks like my little red vector has a smaller length than my black vectors do. And again, all that indicates is, hey, if we're talking again about wind velocity, it says the wind's not blowing as fast, and it's definitely blowing in a different direction. Okay, the direction again indicated by the arrow. So that's vectors. Let's talk about a few things here. Let's talk about adding vectors. Okay. Adding vectors. And the thing with vectors, the way I always thought about it is kind of the tip-to-tail method is the way I think about it. So let's add vectors, and let's talk about them graphically. Suppose vector u is just a vector that moves horizontally to the right. Okay, so that's supposed to be directly to the right. And suppose vector v, suppose that vector is pointing, kind of up and to the right. The idea is if we add the vectors, vector u plus vector v, the way that you get a graphical representation, so when we add two vectors, we get a new vector. So just like when we add two numbers, we get a new number. When we add two vectors, we're going to get a new vector. And all I want to do is just make a graphical connection as to what this vector will look like. And what you do is, whatever vector you see first, so I see vector u first, I'm going to draw vector u. Okay, so I'm going to draw u. Okay, so again, forgive my poor artistry. So here's vector u. Now what we do is we're going to add on vector v, and all we do is we just take the tip of v and we glue it on to the end, the tail of u. So here's vector v. I'm going to glue him on. And what we do is, so if you kind of think about it, we started with u. This is kind of the starting point. V takes us up to here. This is kind of the stopping point. What we do is we make a vector that starts at u and stops at wherever v took us. Okay, so there's a new vector, and this new vector that I've drawn would be the vector u plus vector v. Okay, so maybe let's do another vector addition problem. Let me add 3 of them. Suppose that's vector u, vector v. Suppose vector w is just a vector pointing straight down. Okay, so now if we do the same thing, if I take, and let's make vector w a little bit longer. Okay, so if I take vector u plus v plus w, again, I just do the same process. I'm going to draw a vector u. I'm going to now glue on vector v. And then it says next glue on vector w. So v stopped right here. I'm going to glue on vector w. It's pointing kind of due south. And again, now I just play connect the dots. I started at this point. If you kind of think about following the arrows, you stopped at this point. You connect where you started to where you stopped, and that would be the new vector, vector u plus vector v plus vector w. Okay, you can actually show, you can give a pictorial argument that if you switch the order around, that if we draw the vectors in the order w plus v plus u, or maybe we do u plus w plus v, it actually turns out that no matter what order we do them in, they're going to take us all to the exact same place. So just like with numbers, the order in which you add 2 vectors doesn't matter. Okay, so that's kind of a graphical representation of adding vectors. Well, what if we multiply a vector by a scalar, just by a regular constant? It's probably going to do what you think it would do, which is just stretch it out or kind of contract it. So if this is vector u, this would be vector 2u. I just basically make it twice as long. So there it is once. Let's glue it on again. So that looks to me roughly twice as long. That would be the vector 2u. If I took, say, 1/2 of vector u, just chop it down to half its size. Notice all that's happening when you multiply by a positive number. It's just going to stretch it or contract it. It still points in the same direction. However, if we multiply by a negative, so suppose I take -1 times vector u, it's going to stay the exact same length. Okay, so the length doesn't change, but what it does is it reverses its direction. So 1 times vector u, it would keep the exact same length, but now instead of pointing directly to the right, it's going to point directly to the left. And the same thing, -2 times u. So to me, the negative basically says reverse the direction, and then stretch or contract accordingly. So -2u would be the vector that points to the left, but is twice as long as the original vector. Okay, so if that is what it means to multiply by a negative, let's talk about, again, one more vector problem. So let's do vector u just like it was. We had vector v, kind of looked like that just a second ago. Again, forgive my poor artistry. What does it mean to take vector u minus vector v? Well, the idea to do vector subtraction, all we have to do is we can write, so we leave u alone, the idea is now we can write this as plus the negative of vector v. Well, if this is our vector v, then that would tell us that the negative of that vector, again, it keeps the length, but it just changes its direction. So now we can think about it again as being vector addition, just like we did a second ago, and we can do the kind of tip-to-tail procedure. So again, vector u pointed to the right, vector v, if I glue that on, now it's going to backtrack to the left and down a little bit. So there's vector u, there's vector negative v. If I take where I started to where I stopped, this new vector in red would be the new vector u minus v. Okay, so that's kind of a graphical representation of vector addition and scalar multiplication. I think I'm going to stop this video here. In the next video, I'm going to talk about vector addition algebraically, scalar multiplication algebraically. I'm also going to talk about components of a vector, and then finding a vector representation of a vector that goes through points A and B. So I hope these examples make some sense. Again, as always, feel free to post comments and questions, and hopefully I can clarify things or somebody else out there can.